All right, hello everyone. Today we're going to continue with our electricity discussion. We're going to pick back up on Ohm's Law, which really just is Ver. All right, remember V equals IR. All right, so a simple review of this stuff. We have voltage equals current times resistance. All right, now what these things mean is, remember, voltage causes current to flow through a resistor. All right, or to flow through wires, to flow through a light bulb, whatever. We'll talk about what that actually means. All right, but voltage causes current to actually flow through the things. So in a simple problem, a simple Ohm's Law problem would be something like you hook up a 50 ohm resistor. So there's your 50. All right, and that could be a light bulb, whatever it is, 50 ohm resistor to a 100 volt battery. All right, and the question would be how much current flows through that resistor, how much current flows through that light bulb. So it's pretty simple, where we would just take the 100, all right, volts, plug it in for V, there's our 50 ohms, and then we just solve for I by using algebra, and you see you're going to get 2 amps or 2A of current through that resistor. All right, that's the simple way of using Ver. Now, what does this look like a little bit more in a physics lab? What does it look like in real life? Well, let's talk about that stuff now, all right? So let's start with the voltage part of it, all right? Remember, voltage is an electric potential difference. It's determined by not just the voltage in one spot, but the voltage in two. And we started with these two things, positive voltage and negative voltage. And the difference between those will give us our overall V for invert. All right, but we're not going to use these things. Somebody, runs their electricity in their house with these two charged rods. All right. Now we also talked about the V invert being a battery. All right, we got the positive and the negative, and the difference between those 2 points gives us our overall voltage. All right, but we're not going to use. We can use these in real life, but for our demonstration on our lesson here, we're not going to use these for several reasons. One, we can't change the voltage. All right, that's already set. And two, these things will run out, all right, and they cost money. So we don't want to use them all the time in our lab. What we're going to use to supply our voltage is this big thing, all right? Now they got a couple like plugins over here, but these two plugins provide our positive and our negative, or our electric potential difference. All right, we hook them up these things, and that gives us our V invert. And the nice thing is we can turn it on and off, all right? And it's got a knob here. And we can see what our values for the voltage is going to be set to by just adjusting this thing. So that allows us to adjust our V in volts, all right? And that's going to supply our V from Ver. That causes the current to move through things. Now, current is going to be moving through wires. We're going to plug these things up, and the current will be going through those wires because this thing is hooked up to a voltage. All right, now the R. The R invert, all right? We're going to use actual resistors, all right? These things right here supply our resistance, and it has a particular value, all right? It's pretty boring. Nothing really happens with these things. They just cause the R invert. How you can think of this in real life, this can represent your light bulbs or anything that you plug into your household circuit, which we're going to do, anything that requires electricity, you can imagine as being represented by these resistors. All right. So again, this causes the V. This supplies our V. All right. Invert. This is our R invert. All right. And the current moves through wires and moves through this resistor. Now, these wires do have some resistance to them, but we're going to say it's negligible, all right? So we go back to this thing here real quick. We could say, for this example here, this big old box, all right, we could set to 100 volts. And if this thing had a resistance of 50, then we would get 2 amps of current moving through this and the wire, all right? Now let's actually build a circuit and see how we can start working with these things. Okay, so before we start building and working with circuits, regardless of whether they're building them in real life or working them on paper, we have to understand a couple symbols and instructions or slash blueprints for building these things. All right. So what we have here is a diagram of a circuit. All right. There's a couple things in here that now they're in symbol form. All right. This one here, all right, represents our voltage box. All right. In other words, you can almost think of it as this is the V invert. It gets a little bit more complicated, but that's all right. We'll deal with that. All right. This is all. You can also think of this as your battery. This is your outlets in your house. All right. Now these lines here are just wires. All right. And this symbol up here is our resistor. All right. So what we can see here, we have our voltage box. We have one wire going out, hooking up to a resistor, and then another wire going back down into the voltage box. All right. So that's the diagram. Let's see what that looks like in real life. All right. So let's build this circuit here. Just a reminder, here's our diagram. All right. Now, this is this box, and notice we have one wire coming out. All right, I know it's kind of hard to see here. We're gonna have one wire coming out of this thing. It doesn't matter what color. And then we add that wire follows along to a resistor. All right, there's our wonderful resistor. Notice I had to use alligator clips to hook it up to the wires. And then leaving the resistor, I have another wire, right, that goes back down into this voltage box. And if I turn this thing on, I'll have current that's going to flow through here, and it's terribly exciting. All right. Now, I don't have it plugged in right now because if I turn this thing on, you will see nothing happens. All right. It's just a resistor. If I had a light bulb here, I'd turn this thing on, the light bulb would light up. All right. So let's see what we can do to test to make sure that Ohm's law works for something that's built like this. All right, now to do that, we're going to have to add in a couple things to measure some of our components of Ohm's law. We're going to have to measure the volts, and we're going to have to measure the current to make sure everything's working. All right, the resistance of this is already set. We'll talk about that as we go along. All right, but let's first see a couple different components that we're going to also need to add into this diagram, and that we're going to have to use in our real life circuit here. All right. Okay, so the first thing we're going to add into our circuit is something that's going to measure the current. All right. And what that is called is an ammeter, because it measures the amount of amps going through here. All right. So this symbol looks like this. All right. And you can see that the current would flow through the wire and then flow through the ammeter before it goes into the resistor. All right. So the current's going to be flowing through the ammeter, and then that can measure how much current. What we're going to use for that is this. All right, it's a multimeter, so it can do a whole bunch of things, but we're going to make it an ammeter. All right, so an ammeter measures the amps, so it measures the current. It tells us how much I there is in Vert. All right, now our other thing we're going to use is a voltmeter. All right, and a voltmeter obviously measures the volts between any 2 points. Remember, the V invert is between any 2 points. There's got to be a difference in them. All right. So this point here, this point here and this point here each have different voltages, and the difference between those 2 points is the actual V invert. All right. So since we have to measure 2 points, we use another ammeter, but now we're going to make it a voltmeter, and it has 2 wires coming out where there's just probes on the end. All right. So these probes here can touch one point, another point, and the difference in electric potential, all right, is, in other words, the difference in the volts between this one, difference between the volts and this one, is our V invert, all right, and that would show up on here. So what it would look like when I build this thing for this diagram, I would take my voltmeter, all right, and I would touch it to that point, or that point to that point. Sorry, that's upside down. There we go, that's a little better. If I touch it to that point and that point, that will tell me the voltage of this battery. If I touch it from that point to that point, it'll tell me the voltage at which this particular resistor is hooked up to. Now you can see in this one, this wire is directly related, directly hooked up in this spot. So that spot and that spot are gonna have the same voltage since there's nothing in the way. The ammeter doesn't affect anything, it just measures a current, all right? Now, if I turn this voltmeter on and touch this, if I touch this literally, it's going to say nothing, because this is just a drawing, all right? But we are going to turn these things on and do the actual lab just to make sure all this stuff is working, all right? Okay, so here's our built circuit with an ammeter involved, all right? You can see we have our voltage box here, all right, wire coming out. It's going into the ammeter. It's coming out of the ammeter. You can see it goes under there. It's hooked up to our resistor, all right, and it goes back in here. Now our ammeter says we are getting 0.06 amps through there, all right? And so that's our I invert. Now, to get the V invert, we must use our voltmeter, which is the orange one here, all right? And we have to touch both sides, all right? And when we do that, notice it'll fluctuate a little bit, but we got about 6.25 volts is what we're getting through there, all right? And now we can use those numbers, so 0.06 and 6.25, to figure out the resistance of our resistor. All right, and I'll show you what that looks like in a sec. I know this is kind of hard to see, but I'm just one person trying to get this done, and I don't exactly have a cameraman handy. All right, so here's our amps. Remember, the current's flowing through there. This thing is providing the voltage, and we can measure how much voltage that thing is providing by touching that to each of those two sides. We see it's 6.25 volts. All right. All right, so if we put that little lab into diagram form, essentially looks like this. There is our voltage. Our ammeter measured 0.06 amps, and when we touch the voltmeter to either side to get the voltage across this thing, in other words, what voltage this was hooked up to, it gave us 6.25 volts, all right? That's essentially what we just saw there in real life. So how do we use that? Well, we just go back to Ver, all right? We knew the voltmeter, the voltage was 6.25. We plugged that in for V. We know the current was 0.06 amps. Plug that in for I. And then we can solve for R using algebra. And we see that it's about 104 ohms, which is the actual value of that resistor. I have it listed as 100. So there's a little bit of rounding. These aren't the most accurate instruments, but that's how we use Ver. All right. So the idea is for a simple circuit like this, all right, how you can relate this to your house is this is your outlets in your wall, all right, that you plug in whatever you need to, all right? And whatever you're plugging in is represented by that resistor, all right? And so that resistor gets that voltage, is hooked up to that voltage, and the current will flow through whatever that thing is you plugged in here, all right? If it was a light bulb, all right, the more current going through the light bulb would give you a brighter light bulb. That's essentially how that would work, all right? So we're going to look at a little bit more complex ones, but that's how Ohm's law is applied to basic circuits. And now we know the parts of our circuit. We have our voltage box, we have our wires, we have our ammeter, which measures the amps. We have our resistors, which represents light bulbs or really anything that you want to plug into an outlet in your house. All right, and then we can measure those, how much voltage those things are getting with our voltmeter. All right, so let's see a little bit more complicated applications of circuits, which is what we're dealing with. All right. All right, now we've seen a basic simple circuit, and we saw how Ver applies to that. Let's move on just a little bit. All right. So there's basically, we're going to start adding in multiple resistors into our circuit. It's like having multiple light bulbs or multiple things plugged in your house. How does that all work? Because you don't just have one thing plugged in to your household circuit. All right. So what we're going to do first, and basically there's two ways that you can hook something up into an electrical circuit. All right. We've already done this one, but if we get multiple resistors in there, multiple things hooked up in the circuit, one way you can do that is what we call wiring them in series, which looks like this. All right. Basically, series means only one path for the current to take. All right. We see the current can come out of here. It's going to go through that ammeter. It's going to go through both those things. There's no other path for that to take. All right. So how is our overall circuit affected by wiring something in series? All right. Well, let's take a look. We can build this circuit. all right? Just one resistor with a wire going in another resistor, and then it goes back to the battery. All right, so let's build this and turn it back to our same values as before and see what happened to the current and the voltage and resistance and so on. All right? Okay, so in this circuit, I set the voltage box back to what we had before at about 6.25 volts, all right? And you can see our resistors are wired in series. There's one path. The current goes through this wire, goes through that resistor, goes through that wire, directly into there. There's nowhere else for it to go. Then it goes to our ammeter and back here. And now look at our ammeter. Our ammeter is now 0.03. It was 0.06 before. So what that tells me is when I added these resistance in, the overall current went down. All right, the overall current went down, assuming that the voltage was the same. All right. Now, what we can do is measure our voltage for each resistance and see what happens. All right. So if we measure just the voltage that this one's hooked up to, all right, it's only 3.18. This one over here, when I touch these there, we get about 3.2. All right. So notice, yeah, these are the same, but there are less than it was originally. Now remember our total voltage, which would be from, and I'll show you what that means in a diagram, but if we touch this one all the way to the beginning of this one, which is kind of hard, let's see if I can do that with one hand, there to there, and notice we get, let's try that again, about 6.4, 6.36, all right? All right, so let's put all those numbers together and on on paper and see what that's kind of telling us. All right, to see that circuit and diagram form, it's essentially this. There was our voltage box. There was our ammeter, which only read 0.03 amps. We measured the voltage for each one. All right, in other words, we touched the prongs to each side of each resistor. And then we also got the total voltage by touching the beginning to the end. All right. Now notice a couple things. All right, with those values, we start applying Ver. All right. If we apply Ver to each individual resistor, we'll have 3.2 volts for one resistor. And we know the resistance of that one is 100, and so it gave us a current reading of 0.03, which makes sense. So that solves for 0.03, which tells us the current going through that was 0.3 amps, which is exactly what our real life values were. Notice it's one current going through both of those things. All right. So we did Ver for the other one, we would get the same thing. It would tell us that there's 0.3 going through there. Now, if we look at their individual voltages, all right, 3.2, 3.2, well, if we add those voltages up for each of them, we get 6.4 volts total, all right? And when we measured that back here, we added this one's voltage up, that one's voltage. In other words, it's a weird idea that they can have different voltages on what they're hooked up to, but that's fine, don't worry about that. But if we, what that essentially does is regulate the amount of voltage going through, regulates the current going through an individual resistor. If we had different values here, we would have different currents. And we're going to see that in a different lesson when we learn how to work on circuits with pencil and paper instead of building it all the time, because that can be kind of annoying, all right? So essentially what we need to summarize for resistors in series, all right? The current through each resistor is the same because there's only one path for it, all right? But the voltage, the individual voltages will have to add up to the total voltage. And maybe the most important thing is that we saw from when we had one resistor to then when we added two resistors. But we add them in series. We had one resistor, we added a resistor in series with that first one. We can see that the more resistance, the more resistors, the less current we have. When we only had one resistor, all right, hooked up to 6.5 volts, all right, in other words, the voltage box was 6.5 volts total, we had 0.06 amps. But when we hooked up two resistors in series to that voltage box, which stayed at 6.5 volts, the current went down. More resistance, less current. More resistance, the lower the current. All right? So now let's look at the next way, or the other way, where we can wire these resistors. Okay, so the other way we can add resistors to a circuit is by adding them in parallel. All right, and this is what that diagram looks like. They don't literally have to be drawn parallel, but that's kind of how we describe it, and we'll get into that a little bit later. But notice that essentially the current comes out of the voltage box, right? Goes through an ammeter, so we can measure that. And when it gets here, now the current can decide. Some of the current can go up here through that resistor. Some of the current can go down through that resistor, and then they'll join back over here. All right. Now let's see what that looks like from a building point of view. Okay, so here's our parallel circuits. It's very hard to follow, especially just through on camera, but I'll try to walk you through it. I have it turned on, and then we have one wire coming out. And now notice this wire comes down to here, right? And then splits up into two branches. We got the black branch here that goes through a resistor, and then we have the red branch here that goes through a different resistor. And if you follow along, these two branches connect back to each other. All right, connect back to each other, and we have one branch leaving, one wire leaving, goes into our ammeter, and then our ammeter goes into our circuit here. All right. Now notice in this one, our current is 0.1 amps. All right, 0.1 amps. And what we can do is, I could build ammeters through here, but it's a little bit too much. It's hard to get on video, but we can still figure out our voltage that each one of these are getting. All right. So this one we have it hooked up to, let's see if we can get that going. I know it fluctuates, but that's because I'm not holding it too well. About 5 volts. All right. And then this one is hooked up to about 5 volts as well. All right. And notice that this one over here is like, let's change that a little bit. If I increase this back up to our 6, like we're used to. All right. Now notice, let's do these numbers. We have 0.12 amps total, and we're back to our 6 volts, just like we had our other ones. All right. Let's give it a little more if we can. About 6, all right, if I can get them touching the right way. And then this one is at about 6. All right, a little bit low. Maybe we can increase it just a little bit. All right, so we got 6 volts here and about 6 volts there, like before. And we're still at about 0.12 amps. All right, so let's see how that plays out on paper, and we can figure out what's exactly going on here. Okay, so if we start applying Invert to the data that we recorded, all right, if we take each individual resistor, we can look at it this way, all right? Notice both resistors had a reading of 6 volts on the voltmeter, all right? So if we use Invert for each of those, we can see that each resistor is getting a different current. Now in this circuit, I used 2 different value resistors. One was 100, one was 60, one was 100. All right, so it makes sense that they had different currents. If you go back and look at the diagram, imagine your current coming through here, right? You get to this spot here. Well, where would you want to go? Would you want to go the path that has high resistance or the path that's less resistance? Well, naturally, you're going to go through here. So most of them are going to want to go through there, but not all of them. Some are still going to go here. It's kind of like going in a line at an amusement park. All right, there's some times where you get to a line, as you're going through the line, right, and you have a decision to make whether you want to go left or right. Now we know the final destination is the ride. You're going to get back there, but you can take 2 different paths, all right, one this way, one this way. Well, if you see the one line is moving fast, then everybody's going to go that way, all right, until that one gets overloaded, and then some people are going to go the line that's moving, that has a little bit more resistance, but there's not as many people there, all right? So they're going to take the path of least resistance, but only to a point, all right? So this one, not as much resistance, and more current's going to go through here. This one, more resistance, so not as much current's going to go through. But if they all try to go through this one, that wouldn't make any sense, and then they would get overloaded. So some of them would still have to go through here. All right. So notice when we put those two together, we still get the total current. Now I know here it says 0.15 amps, and we had about 0.12. There's, they're not the best measuring device. They're not the most accurate. So the idea is that the current splits up, not necessarily equal, depending on resistance, but it comes back to equal the total. All right. Also notice that in this case, and this is maybe the biggest point, is that when we had the resistors in parallel, the total current actually went up. All right, so to summarize, in parallel, when we wired in parallel, the voltage, the voltmeter for each of those things were the same, and it equaled the total voltage. All right, so they both got 6 volts, regardless of what the resistance was. They both got 6 volts, but the current can be different, and the current's going to add it to be the total voltage. And maybe this, and I think this is the most important point of all right? Notice when we added in another resistor to this one, the current went from 0.06 amps, which what it was for one resistor, all the way up to 0.12 amps, all right? And that's kind of weird. We added more resistance, but somehow we got more current out of it. All right, that's a weird idea, but that's maybe the most important thing to take away from this is when you add resistors in parallel, you actually get more current. All right, more current. So how does that make sense? How can you add more resistance, but yet current can go up? All right, well, it's a pretty simple analogy. All right, let's imagine you're driving on the highway and you have to hit the tolls. All right, well, if you have one toll booth, you got this. All right, so now our toll booths represent our resistors. So if we want to add in more toll booths, if we add them in series this way, well, what's going to happen to the overall traffic? The traffic is going to be worse. It's going to be slower traffic. In other words, a lower current. All right. So once we get to this one here, this car would have to wait for the next one, and the overall traffic would be worse. All right. That's in series. It would be worse. Instead of building our toll booths and, in other words, wiring our resistors like that, what if we do it this way? What if we have them, if we want to add a resistor or a toll booth, we can give another path. Well, what if we do that? What's going to happen to the overall traffic? Well, this car can go here instead of that second car waiting for this one. He can go here and just go through there. And by the time that third car comes up here, maybe it's gone, and that's going to increase the traffic flow. So now we're adding more booths, but we're getting better, faster traffic. In other words, a higher current. And it works the same way with our electrons, our current in our circuit. All right, so more resistors in series means lower currents, all right, a higher overall resistance. And if we add more resistors in parallel, then we get actually more current. It actually decreases the overall resistance. And we're going to do a different lesson where we kind of see how these numbers work out and how we can apply some equation, a little bit more equations to these circuits. That's a different lesson. This is just to get the overall idea of building basic circuits and starting to get an idea of how like a household circuit is wired, all right? Because you use electricity, you use circuits all the time. You may not even realize it, and this gives us an idea of what's actually going on there, all right? So thanks for watching. I'll see you when I see you.